So, before we move on to our syllabus, let us look at this last decade, which has seen a tremendous amount of interest in machine learning. So, I am calling it a decade of machine learning, and the reasons for that are as follows: that we have seen an explosion in the amount of data available because of the internet, and the computing power available has been also growing. And there were some recent advancements in neural network training algorithms, which has given a lot of impetus to machine learning, especially when it comes to neural networks. Somehow, it is given an impression to many people that AI is only ML, but let us see why that has been happening in the last uh, 10 years or so, before we move on to our topic, which is problem solving using search, I think. So, let us start with neural networks. It is not a new technology. The whole idea is based on the fact that collections of simple processing elements can do complex things. So, sometimes people call this as emergent systems and so on. And a neuron is basically a simple device that computes a function of the inputs it received. So, in the figure on the right, you can see that there is this circle is the neuron, and it receives n inputs x 1 to x n, and it computes a function y is equal to f of x 1 x 2 up to x n. It has been discovered that this function has to be non-linear. Typically, it is a sigmoid function, but putting together large collections of such neurons can do fairly complex computations, and the living proof for that is our own brain, which is basically also made up of very simple neurons, but there are billions of them in our brain essentially. Now, one of the earliest neural networks that was devised was called the perceptron, invented by McCulloch and Pitts in 1943. It was a single layered neural network designed to be a binary classifier. By a binary classifier, we mean it can distinguish between two classes essentially. Holiday, not holiday, or whatever you can think of, healthy, non-healthy, any two classes it could distinguish, and it was a linear classifier. So, that was shown by Minsky and Pepper in 1958, that it could classify only linearly separable classes. So, for example, as you see on the figure on the right, there are 4 data points, 2 are shaded and 2 are not shaded, but we cannot draw a single line which will separate the shaded data points from the unshaded data points. So, perceptron was unable to do that, but then people discovered the hidden layer. Rumelhart, Hinton and Williams, they showed that a multi-layer perceptron could be trained to learn any non-linear classifier. So, this is the idea of a multi-layer perceptron, or feed forward network as we call it now, where in this example there are 3 layers. There is one input layer on the left, one output layer on the right, and there is a hidden layer. And what was shown was that such a neural network can learn any function essentially, any classifier essentially. They also popularized the backpropagation algorithm, which is used to train these feed forward networks. The idea of backpropagation is to look at the output and look at the desired output, take the difference and propagate it back into the network, and you go around adjusting the weights in the connections. So, everything that the neural network knows is stored in the weights of the networks essentially, which is different from what we want to do in this course, which is symbolic representations, where we have symbols for whatever we want to represent. Then Hinton persevered with neural networks and showed in 2012 or something that deep neural networks with many hidden layers, they are very efficient and they achieved phenomenal success in computer vision. They could recognize thousands of types of objects, for example. So, let us look at what these deep neural networks look like. You can compare it with this simple idea of a 3-layer network with one hidden layer. Of course, I have drawn only two neurons in the hidden layer, but in principle you can have as many neurons as you want. And the number of neurons will depend on the size of the input that you are taking. So, for example, if it is an image, if it is a 10 by 10 image, 10 pixels by 10 pixels, then it will have 100 pixels. So, then the input should be size 100. but this is just a schematic essentially. And the output will show what are the different class labels that you want to show. In this example, I have shown 3, but you could have more, I think. And that is what modern day deep neural networks with computer vision have done essentially. So, this is a schematic again of a deep neural network. I have drawn the connections so that they look neat, but in principle from one layer to the next there could be any number of arbitrary connections, and essentially the weight of the connection is what decides what the connection really is. If the weight drops to 0, it is like not having an edge, but otherwise the connections may be anywhere. And we have said that these are feed forward neural networks, and information flows from the left to the right, the way we have drawn it, assuming that the leftmost layer is the input layer, the rightmost layer is the output layer, and then there are fairly large number of hidden layers essentially. So, this is a general architecture of a deep neural network. More recently people have come up with more specialized networks and things like that, but we will not have time to go into that. So, what happens in a feed forward neural network? You show an image to the input layer, and on the output layer one of the nodes lights up, so to speak, essentially. It is like identifying which of those 5 categories or classes is being seen in the image essentially. Now, in this example I have written the words horse, cow, giraffe, bear or lion, and it may be that we are seeing pictures of animals, and the neural network, you show it a picture of a horse and the topmost node in the output layer will light up. If you show a picture of a lion, the bottommost layer node will light up. How does that happen? That happens through a process of training. We have already mentioned backpropagation algorithm, and the way backpropagation works is, this is called supervised training. You show an image at the input layer and you tell the system what is the expected output, and then the system may have computed its own output. You take the difference. So, because all these values of activation are numbers, you take the difference between the expected and the input and send it back through this algorithm called backpropagation, which goes and changes the weights of the networks. If you show hundreds and thousands of such images, eventually the network learns to distinguish between these 5 categories: horse, cow, giraffe, bear and lion. The fact that we are calling it horse, cow, giraffe, bear and lion is just between us. As far as the machine is concerned, there are 5 output classes. We could have called it class 1, class 2, class 3, class 4, class 5. It does not matter to the network at all. All that matters to the network is that if you show a particular image, which class should be identified. So, we could have shown images of scenery, for example, then it would say there is a tree in the picture, there is a river in the picture, or sky or hill or grass, or we could have shown fruits and then it could have identified one of the 5 fruits. So, in this example there are 5 classes, but in general you could have any number that you want to work with, and that is what the deep neural networks research and development has shown. And because of their work, these 3 scientists, Hinton, LeCun and Bengio, they were given the Turing Award in 2018. Turing Award is the highest award you can get in computer science. It is considered to be almost equivalent to the Nobel Prize. Now, let us look at what is happening in deep neural networks. So, if we are interested in building an intelligent agent, okay, which senses the environment and does something and maybe acts upon it also. So, we had identified that there are 3 layers. One is signal processing, then there is the neuro-fuzzy reasoning, which is where the neural network sits, and the third is symbolic reasoning, which is what we are interested in this course essentially. So, to a neural network, in particular to a deep neural network, if you show a speech or data or or any kind of data as input, it will produce a symbol as the output. We saw that there were 5 possible symbols in the previous illustration, and it could be any number of things, but we must keep in mind that a symbol is a perceptible something that stands for something else. We will come back to symbol when we talk about symbolic reasoning, but one must keep in mind that it has no intrinsic meaning essentially. So, if you are saying that it is seeing a horse, then it is only because we have labeled that output node as a horse, and there is nothing more than that essentially. So, we can use this ability to classify images or speech or other kinds of data to do all kinds of things. We can identify, for example, as we said, horse, sky, tree. We can identify a disease like breast cancer, for example, or we can recognize people. So, we can recognize some whose picture is being shown here essentially. So, I must say at this point that especially in the case of identifying diseases or classifying diseases or diagnosis diseases based on some kind of an image essentially. So, you look at an image, for example, your doctor may look at your X-ray or your radiograph or maybe an ultrasound image or just a photograph of your eye, as we will see in the next example. And by looking at the image, the doctor can give a class label that this particular disease is present or not present or things like that. By the way that neural networks are trained, you can assimilate the experience of hundreds and thousands of doctors. If they have labeled certain images, you can use that as a training data and train a network essentially. So, I said that a user shows an image and gives a class label. It is not as if the process is happening online. You can just prepare a large data set with image and class label, and thus the system just runs through the whole thing again and again. Now, because of the fact that neural networks can learn from the experience of many doctors, it has turned out that in many of these tasks and as was shown by Cambridge University recently in the case of breast cancer, these machines perform the professional radiograph image readers or doctors for that matter. So, it is definitely a big boon for medical science. But the question that we will want to ask in this course is that fine, you have managed to identify something or label something, what next? So, we will be focusing on next, and I am sure you will have opportunities to study deep learning in more detail somewhere else. So, this is just again to illustrate why deep learning has been good in diagnosis, and this is an example of a app called Face to Gene, which is being used by doctors. So, you just take a picture of a child and upload it on the app, and it identifies, you can see, you can kind of click on things like compare images, or you can say do diagnosis, and here it is showing Down syndrome, for example, and it could show you what the images are. And this app is a very successful app, and as mentioned in this article from NBC News, that for example, the Mowat-Wilson syndrome, which is not so easy to identify for many doctors, could show up in this app essentially. So, this is just again to endorse the fact that deep neural networks are very useful in many situations. So, essentially what we are doing is image labeling, that is what I am trying to highlight here. And if you look at the colors, so suddenly I have changed the sizes of the circles here. The lavender or pink or whatever you want to call it, the intermediate layer has become much larger, and the cyan or the greenish circle has become much smaller. That is in some sense the architecture of our current deep learning algorithms essentially. And what they can do, they can take an image, do the signal processing, do the neural network, and come up with labels like tree, grass and sky for this particular image. As I have said, it can also be used for face recognition, and many governments around the world are actually using these kind of machines for surveillance of people essentially. Now, when we interact with the internet, and you see this, all these people on the left hand side of the figure, they are like eyeballs, and we are interested in some topic, of our interest. Maybe it is shopping, maybe it is we are learning some subject or whatever the case may be, but we are the ones who are accessing the internet. But what we are trying to show here is the internet is also observing you at the same time essentially, or internet, by internet you mean whatever the big company it is, it could be Facebook or Google or Amazon or Microsoft or whatever. They are looking at all these people, looking at them and treating those people as data. So, we end up being data for the machine learning algorithms used by these big companies, big tech companies. and they of course then want to use that data for some way of making money. After all, big companies are there to make money, and one of the main uses they do is to help their clients place their ads for the appropriate people, that this person may like to buy this iPhone, or this person may like to buy this kind of a camera, or whatever the case may be. So, you must keep that in mind, that when we are interacting with the internet, we are the data, and they are kind of classifying us. But people have observed that what machine learning does, all these things that we have talked about, speech recognition, image processing and so on, pattern recognition, are animal like abilities, in the sense that whatever they do, animals can do in a blink of an eye. So, you can search for blink of an eye, in the blink of an eye on the internet, and you might get some instances of this kind of comments. But a paper which was published in 2018 by Darvish on human level intelligence or animal like abilities, he lists various things that animals do equally good or better than us, essentially. So, he has quoted Julia Pearl, who is also a Turing Award winner, by the way, who said that eagles and snakes have better vision systems than we have, essentially. And other people have said that cats have superior navigation abilities, dogs recognize and react to human speech just as we do. African grey parrots can mimic human speech. What Darvish is trying to say in his article is that fine, we have these machine learning algorithms, deep neural network algorithms, which can do all this kind of pattern recognition. But is that what human beings are differentiated for? He says that none of these animals have the cognitive abilities and the intelligence typically attributed to humans, essentially. Because when we talk about humans, we talk about cognitive abilities. Rene Descartes had famously said, cogito ergo sum, which says, I think, therefore I am. So, if you ponder over this a little bit, we can see that us humans are different from the rest of animal world, in the sense that we plan our lives, we have collective approaches. So, for example, we have diverse societies, you have a tailor, you have a barber, you have a computer scientist, you have a singer, all kinds of different professions who contribute to the good of everybody else, and only we have managed to do this kind of diversification of the society. Only we accumulate wealth, not only for us, but for our future generations. We build houses, we have all kinds of things, collections of books, collections of music and things like that. All these are because we can act intelligently in the world in some sense, and these are the cognitive abilities that we would like an intelligent agent to also get, that they should be able to act in a goal directed autonomous manner and pursue. They should have goals first to start with. Most animals do not have a goal, they just live a happy contented life, go eat and sleep and procreate. Humans, as humans, we seem to have a lot of goals, essentially. We want to have a very high paying job, for example. Now, performance versus competence. So, neural networks are good at some things, and Rodney Brook, who is also a well known computer scientist, has written in this article called The 7 Deadly Sins of AI Predictions in MIT Technology Review. He says that now supposing a person tells us that a particular photo shows people playing frisbee in the park, we naturally assume that this person can answer questions like, what is the shape of a frisbee? Roughly how far can a person throw a frisbee? Can a person eat a frisbee? All kinds of general world knowledge that we carry with us even when we process these images. Now neural networks do not have this background general knowledge. They have been trained over a certain set of images, and they know how to classify those images. So, there is a difference between that, essentially. So, Rodney Brook says that computers that can label images like people playing frisbee in a park have no chance of answering these questions, because they have no idea what a person is to start with, that parks are usually outside, that people have ages and they grow older, and older people look different and all that kind of stuff. and that weather is not something more than just photo to classify. Machines don't have this. They have just learned the mapping between the input image and the class label, and that is what they can do. Marvin Minsky also has a word to say about this. He calls words which carry a variety of meanings as suitcase verbs, and he says that learning is a powerful suitcase verb. It can refer to so many different types of experience essentially. When people hear that machine learning is making great strides in some new domain, they tend to use as a mental model the way in which a person would learn the new domain. So, when we hear about machines doing great work in machine learning, we think that they are learning like we learn essentially. But Minsky says, however, machine learning is very brittle and it requires a lot of preparation for the human researchers or engineers, special purpose coding, special purpose sets of training data, and a custom learning structure for each new problem domain. So, for every different kind of classification task you want to do, you have to devise your network architecture, collect the training data and do the training and all that kind of stuff. So, one must not confuse this with the kind of learning that humans do, that a human child learns from the very point when they start growing up. Again, this is not to deride machine learning, it is just to say that machine learning has its limitations, that it has a place in the world of AI, and it is illustrated not better than this example of the game of Go, in which this program called AlphaGo it was developed by a company called DeepMind, a UK based company. It had about 25 or 26 full time people working on Go, including Go players themselves and computer scientists, of course. And the thing about Go is that we used to think that Go is a much harder game than chess, uh, because chess is played on an 8 by 8 board, Go is played on a 19 by 19 board. And essentially a search algorithm would try to see, okay, what moves you can make, or what, in the case of Go, where you have to either place a black coin or a white coin depending on the two players, where to place the coin. So, the choices initially are 19 by 19 and so on. So, the search space is huge, and people used to think that Go is much harder for computer programs, even though chess had achieved success in 1997 when IBM's Deep Blue had beaten the world champion Kasparov in a 6-game match essentially. People thought Go would be harder, but in 2016 DeepMind produced this program called AlphaGo, which did this feat, and it is a triumph of the reinforcement learning approach in games. And in 2018 and 19, DeepMind published more algorithms. So, they published an algorithm called AlphaGo 0, which could learn without human help, and then they produced a program called Alpha 0, which could learn many different games at the same time. We will come back to this very briefly when we look at games, because we will look at board games in this course. Meanwhile, you can go to the DeepMind website and read a little bit about AlphaGo and the other variations. But more interestingly, it has a link to a nice gripping film on this match which was played in 2016 with full cameras from all over the world, very keen to see what is happening. It is definitely worth a watch.